so when we talk about our limits, okay, so part 2 is going to be limits at infinity. So far, every limit that we've looked at, we have allowed, we've let x approach a specific number, and our generic term was the number a, but we didn't allow x to be equal to a. All right, so the idea behind all of these limits was, as x approaches a specific number a, what does the y value of our function approach? Well, it turns out that not only are we interested in approaching a particular x value, such as x is equal to 0.25, but we may also be interested in what happens to functions, what happens to the y value of a function as x gets really big. So I keep going way out the positive x-axis, and I'd like to know what's happening to the function above my head. And so in addition to approaching a particular x value of a, I may also want to approach very, very large values of x. In other words, I may want to take a limit as x approaches infinity. So we can also look at what happens to the y value of a function as x approaches infinity. In other words, as x gets very large. Now, infinity is not a number, it's not a real number, and so that means that I can never actually let x be equal to infinity, but I can allow x to walk towards infinity, and I can see what happens for really large values of x. So I might want to look at a specific example. And so our first example is going to be looking at the function f of x is equal to 2 plus 3x over x. Now, one way that I can analyze this function is that I can start to plug in x values into my function and see what output I get for a y value. So I might create a table for myself. And so I might start with an x value and figure out what that y value should be. So maybe I'll start out with just a regular old number. Maybe x is equal to 1. And so when x is equal to 1, f1 is equal to 2 plus 3 times 1 over 1. And so our y value of our function is equal to 5. All right. Well, 1 is not a very big number. Let's try 10. So if you have your calculator, please plug 10 into your function and see what your y value is equal to. 3.2. You second that? So f of 10, 3.2. Okay. All right, well, 10 is more than 1, but it's not that big. Let's go up to 100. All right, so if you plug 100 into your function, everywhere I see an x, I replace it with a 100. What do you come up with that? What do you come up with? 3.02. You do have a second on that number. Okay, second and a third. Okay. Well, 100 is not really that big. I mean, I can count to 100 in, a minute or two. So let's jump to 1,000. F of 1,000. You get if you type that into your calculator. 3.002. Do I have a second on that number? Okay, second on that number. All right. I'm beginning to see a little bit of a pattern here. It didn't really work with the 1, but it seems to be working with 10, 100, 1,000. I could walk even further. If x equal to 0 is right here, here's 1, here's 10, here's 100, here's 1,000. 10,000 is way down the hall. And so I can plug in 10,000. And my prediction, and you should check this, is that we end up with 3.0002. All right, so this seems to be working. Now, if I got really excited about this, I could plug in 100,000, I could plug in 1 million, 10 million, 100 million, 1 billion. I could plug in 1 trillion. That's a pretty big number, right? Well, so is a quadrillion. And so is a Google. Anybody know what a Google is exactly, besides a search engine?
Like a million to the millionth power or something like that. Close.
So Google is 10 raised to the 100th power. So that means that you have a 1 with 100 zeros behind it. And a Googleplex is a 10 raised to the Google. So 10 raised to the 10 to the 100. So that's Googleplex. And so that's a ginormous number. Huge. Still not really that close to infinity. Okay? But these numbers are getting bigger. And so you notice what's happening here. As x moves toward infinity, the y value of our function seems to be getting closer and closer. Well, every time we add another 0 in here, so this number seems to be getting closer and closer to a y value of 3. And so the way that we would write this is, when we look at that table, we would say that the limit of, what was it, 2 plus 3x over x, as x approaches infinity, is equal to 3. And what this expression means, that the value of our function f of x can be made as close to the number 3 as we want by making x sufficiently large. You want to be within 2 100ths of the number 3? Well, go out as far as x equals 100. You want to be within 0.0002 of the value of 3? Well, walk out to x equals 10,000. And so as specific as you want to be, we can figure out what that x value should be that we have to walk out to.
So to figure these out with the table, can you just assume that as x gets bigger, that 2 is going to be basically negligible? And you just say that the x's will cancel out and you're done.
And so looking at this expression here algebraically, that's a really good way to think about it. And so things that are happening, yeah, if you have a 2 plus 3 times a bajillion over a bajillion, well, if you lost $2 and you owned $3 bajillion, who cares about that $2? That 2 is totally negligible. And so what we'll be analyzing is the largest powers on the top versus the largest values on the bottom. And so those are going to be the things that are going to be important to us on these limits as x approaches infinity. So that's a good observation. Okay, so along with our table, and we're going to talk more about these limits algebraically, but besides drawing a table, we can also draw a picture of the function. And so you can graph this function on your calculator. And if you do so, well, a few things are going to happen. For example, I see that I have an x in the denominator, so my function is undefined when x is equal to 0. And there's no factor in the top. I can't factor out an x, so it's not a whole, but rather it's a vertical asymptote. And if I'm careful about drawing this, basically copying it off of my calculator, I end up with something that looks like this. I've got a curve that from the left side of x equal to 0, the curve drops down to large values of y in the negative direction. And on the right side, I've got this curve that is up above this horizontal line. That horizontal line is occurring at y is equal to 3. So as I walk along the x-axis, the y value of my function is becoming very, very close to the line y equals 3, very close to a height of y equals 3. All right, now, in your college algebra class, you probably learned about that line. You probably learned that it was called a horizontal asymptote. And so here's the official definition of a horizontal asymptote. The line y equal to L is called a horizontal asymptote. Line y equals L is called a horizontal asymptote if either the limit as x approaches infinity of f of x is equal to L, or the limit as x approaches negative infinity of f of x is equal to L. So on this particular picture, what we were analyzing is what happens to the y value of our function as x gets really big, as x approaches positive infinity. We could do a very similar strategy if we're looking at what happens to the y value of the function as x goes toward negative infinity, toward out the left side of the classroom. And so if either our function settles into values close to y equals 3, far off to the right, or far off to the left, then we have a horizontal asymptote. So in our example, we have a horizontal asymptote of y is equal to 3 because our limit as x approaches infinity of this function is equal to 3.
Would this function also have a vertical asymptote?
It does. This function also has a vertical asymptote at x is equal to 0. So functions can certainly have both vertical and horizontal asymptotes. Okay, so I'd like you to look at another function. And so on your calculator, please change your calculator to radian mode. And I'd like you to graph the function g of x is equal to 5 times the sine of x over x. And please graph that function for x values between -10 and +10.